Hey everyone, I wanted to welcome you to the second part of MATLAB, but right now you're looking at a bunch of beams. And if you go to Google and you just look for beam images, this is what pops up. Now, you know, you can see that often they're steel. Sometimes you see that they're made of wood, maybe even laminated wood, and sometimes they're composite wood. There's all sorts of different kinds of things, but beams are designed to bend. Okay, that's really what they're designed to do. So now you continue to scroll down here, you get beam stream and Jim beam, but that's not what we're talking about here. Now, beams aren't necessarily have to be used in some kind of construction space like you're seeing all along here. It might be the most common reference, but that's not necessarily true everywhere. In fact, you can sometimes have beams made out of plastic or even placed out of plastic in a cabinet safety lock. So right here is a beam. It's a cantilever beam with a force pushing down on it, and it is firmly affixed in this location, just like we saw earlier in class a few weeks ago. So beams can come in all sorts of shapes and sizes, as you see. And so we're going to combine the study of MATLAB with an exercise in the study of beams. So maybe we'll get a little head start on materials or strength of materials next year. So here we have our assignment, and uh, we're going to, again, here's the purpose. I already mentioned that. And this is a quick review of beam analysis. For me, it's a review. For you, it's probably brand new. So let's just see that a beam is a rigid member with at least 3 points of loading, or a torque, that's another story, or at least one moment, which is a force at a distance. So something's trying to bend it, twist it, whatever, well, not twist it, but um, load it in 3 places, not just 2, like a tension or a compression, but something that's trying to bend it and break it, just like, bending or trying to break a stick over your knee. Um, Now, stress is a very important concept here, and we can calculate that very, again, I'm skipping over a whole bunch of stuff here, but our maximum bending stress is MC over I, which is M over S. M is the bending moment, the force times the distance of the bending. S is a function of the beam's uh, geometry. And it's a big difference there. Shear stress, though, is tau. Shear is like a cutting type, whereas bending stress literally pulls it apart like you would if you were breaking a beam of a twig or something like that. Whereas shear stress is like cutting it. So there's two ways of breaking it in this way. One's kind of making it slide with respect to each other, or something like this, and that's shear stress. And we calculate that with um, 3v over 2a for a rectangle. It's more complicated for other shapes, but okay. For a rectangle that you saw there, or v over dt, like an I shape. So if you go back over here, so we could use v over dt here, or here, or if it's a rectangle like this, we can use 3v over 2a. V is the shearing force, A is the cross-sectional area. So that's easy to calculate. Well, we'll get there. All that stuff's easy to find. So just that's a quick introduction to the formulas that we're going to be using. Now, deflection is for a simply supported, that's with on 2 ends and a force down the middle. We'll see that in a second. Is PL cubed, that should be cubed, over 48 EI. I guess that's going to be, nope, not going to do it there. Okay. I guess it didn't copy over very well, but it's PL cubed, not 3, over 48 EI. Talk about what those are. And cantilever is similar, PL cubed over 3 EI. So you can see that with the same amount of length and everything else being the same, if it's set up as simply supported, it has 16 times less deflection than the cantilever. All right, cantilever is what we're seeing over here, where it's not supported out here at all. It's just supported on one end. All right. So those are the formulas we're going to use. Don't worry. I'll walk you through that. No problem. But there are three main factors that affect the stress and deflection on the beam. Number one, the loading. Okay, if you don't load it, there's nothing to break. It's not going to break anything, you know. So you calculate using static analysis, and you can calculate the bending moment and the shear force, but also the length of the beam is part of the loading in this case. That's what I'm going to be working with here. Next, the geometry of the cross section. Okay, and I is the area moment of inertia. C is this distance from the center to the outermost fiber. So often, if it's a symmetric thing, it's half the height. That's all, half the height most of the time if it's symmetric. S, as I said, up there, above there was over here. S is simply I over C. So it makes it simpler if you're looking up stuff, so you don't have to do that one calculation. So it's nice. And T is the thickness of the cross section at the middle axis. So if you go to beam images again, so the thickness here is just right across here. And the thickness of like an I-beam is right down the middle here. It's relatively thin compared to the wood. There's reasons for that. I can talk to you about that later, but you know, why they're designed differently with like an eye here and just like a rectangle here. Those are all good questions you're probably thinking, but that's not what I'm going to answer today. Okay, area is simply the area of the cross section. That's easy to calculate. And D is the depth of the cross section, just top to bottom. Okay, top to bottom. All right. And in one of my references here, I should have that shown. Where'd it go? No, that's not it. That's not it. Okay, well, it might be here. Oh, here it is. Yeah. I guess it doesn't actually show it here, but the depth is from top to bottom over here. Yeah, unfortunately, don't show that. All right. Okay, material properties. So now this is material. So this is the loading, then the geometry of the cross section, and then the material properties. What about the material itself? Wood, you know, what kind of wood? There's a lot of different kinds of wood. Steel, a lot of different kinds of steel. Aluminum, whatever. Plastic. Okay, what about these? Whatever material is chosen or needs to be chosen is going to have an elasticity E given by the materials modulus, elastic modulus, sometimes known as the Young's modulus. So it might show up there. And we can look that up here in elastic moduli. I shamelessly took this from Wikipedia. So, but it's pretty good. Usually a lot of good technical information is in Wikipedia. But for our purposes, good enough for government work. And if a design has deflection requirements, that's important because you got to know how much it's going to flex, you know. And then yield strength. Okay, so if you bend it too far, how far is too far? How much stress can this take before it permanently deforms? All right. So now you might you know, if you have a material that's already chosen, that's going to affect the other things, how much load it can take. Okay, or what cross section you're going to have to choose. So that's the flip side of it, or maybe how long this beam can be or whatever it is. Okay, so what we're going to do is I want you to go through and choose a set of dimensions for a cantilever beam. All right, so here's a formula. You can get that formula over, here it is, right here. So I've got these links all set up for you. And so you're going to want the force and the beam length. All right, so choose those two for force and beam length. Excuse me. Now, next, choose a beam cross section and enter the dimensions. Okay, so there's a bunch of different things here. The designation, weight per foot area, and so on and so forth. Just write those things down, whatever. And then choose a metal material. I am going to go through and use one of my favorite materials, and you're not going to use that material. So you get to choose your very, very own. All right, then begin a new MATLAB script. So this is where I'm going to shift over to this here. Okay, so we've got our assignment over on the right and MATLAB script over on the left. Now, you can create a new one. I hope you did. I already did, and I've got some stuff that I was working on before. Okay, so I'm starting a brand new one here. I've already saved it. Do that now. Open it up, save it now. Okay, you got it saved. Good. Next, use sections, headings, and comments liberally. Okay, so I'm going to start it off with my initials, but no, you should use your full name. My name is not Joe Schmo, but it could be, and so use that in there. MATLAB assignment 2 beam analysis. Okay, something like that, but make sure your name is up at the top and it's got a reasonable heading. Okay. So next thing I'm going to do is I'm going to initialize Workspace and command display window. All right, so how do I do that? CLC actually does a couple commands and then clear all, making sure that everything that I did before is going to get cleared out. All right, so that should be done pretty much every single time you write any of these things. Excuse me. Another one of these because the major section, all that was just the beginning. Okay, set up variables and vectors. One of these days I should probably learn how to touch type. So what I'm going to do first. All right, so from here on out, I'm going to let you do all of your own commenting. Okay, I'm not going to do this for you. You comment pretty much every step of the way. So the first thing we're going to do is we are going to, well, we're doing variables and vectors. All right, so we're going to create variables and a vector for the loading setup, another one for the chosen cross-section, and another one for the chosen material. So first thing I'm going to do is I'm going to set up for my loading setup. So going back up here, I've got a force and a beam length. Okay, so force, P, I always like P for the force. And I always like to put units in there. Make sure you stick with the units. So I'm going to do that in kips. If anybody doesn't know what a kip is, well, it's a unit of force. So you probably think that K, at least KI, is kilo. And you'd be right. What's a P? A unit of force with a P. Don't you know? See what I just did there? I pounded because P is pound. So a kip is 1,000 pounds. So we're gonna make that 25,000 pounds. So 25 kips. All right, so I put the semicolon there because I don't want to spew this out quite yet. All right, beam length, L in feet, length in feet. And I want this to be, say, 10 feet long. Okay, that's good. Remember, you're supposed to be commenting, not me. You do your comments. All right. So now calculate the shear force. Okay. The shear force in something like this is going to be, oh, okay, I'm doing it for simply supported. That's right. I'm doing it simply supported. You are doing it for a cantilever. You do it for cantilever. All right. I'm doing it for simply supported. So for me, V which is the shearing force. And I would put that in, talk about that in my comments, but not this time because you're doing it. In kips equals P kips divided by 2. All right, so there's my formula, using a formula there. And then I'm going to calculate the maximum bending moment. Now that I've got that. So if you look over here for your cantilever beam, your maximum bending moment is actually equal to P times L. So your stuff's actually a little easier than mine. Mine's going to be P times L over 4. So my maximum bending moment, M in kip feet equals, remember this kips times feet, so not divided by feet. Sometimes people make that mistake. So I'm going to put this in parentheses, and it's going to be P kips. Oh, I can't spell that properly. Oh, you should misspell something and then see what it does to you, because it's going to yell at you somewhere. P kips times L feet divided by 4. Now, I like putting spaces in there because I can read it better. If you just jam it all together, you start missing things. So that's why I put a lot of spaces in there. It makes it a lot more legible. Okay. Now I'm going to create, now that I've got each of these things, I'm going to create my loading vector. So load simple central. Okay, yours is not going to be simply supported, and it's not going to be centrally located. So your variable is going to be something different than mine. So load simple central equals, and then I'm going to open up in a bracket here, P underscore kips L underscore feet the underscore kips. And if you want to use different units, be my guest. M underscore kip feet. Bracket. There we go. So now I have a loading vector. This vector contains all of my basic loading information. And so if I ever wanted to know what the loading information is, boom, I should be able to access it pretty quickly. It's kind of the point. Okay, now I'm going to set up the beam cross-section parameters. So again, you should have comments all the way through here as to what you're doing each step of the way. All right, so I'm going to use a W30 by 211. All right. Oh, you know what I should do? That's what I'm going to do. I'm going to use a W29 by 198. Okay. You have to find something on the charts and use it yourself. So I'm just going to call it right like that, equals, and I'm going to give it a text thing. So just exactly what it is, W29 by 198. Okay, so linear weight on that, look that up, and mine is going to be lin weight underscore W30 by, W29 by 198 is going to be, oh, I want the units, pounds foot equals, oh, it should be pounds per foot. So I'm going to put a little underscore here. So it's pounds per foot is going to be 200. All right. Next, area underscore, and that's going to be in inches squared equals 60. Okay, next, depth, boink, and that's going to be in inches, is going to be 28.8. And then web thickness, so just call it web thick. Again, you can call your variables whatever you want to, but if you don't use them consistently, then it's going to yell at you and say, hey, I can't find that. So you're going to have to make sure you use all that stuff consistently. And that is going to be in inches equals 0.75. And then flange thickness. Making sure I've got everything consistent. I like making things go consistently because then it's a lot easier to find it in the future. Okay, and that is, okay, so that's the thickness of the flange. So that's going to be 1.3. And then we've got AMOI. So I in the X direction. You don't need to worry about I in the Y direction. Because you're going to have that, but it's not going to be as important. And yes, they are in units of inches to the fourth. Don't try to get your head around that one. Just accept that it's in inches to the fourth. It's like a volume times a distance, but it's it's really an area times the square of a distance, but that's okay. Okay, so we've got, for that one, we're going to have 9,900. And then for section modulus, this is where that S comes in, SX. Here's our section modulus, and that is in inches to the third, but no, it's not a volume. And that is going to be 650. And then our radius of gyration, Rx. And of course, any radius is going to be just in inches or just millimeters or something like that. Nothing squared. And that is going to be 12. All right. Good thing I looked these things up ahead of time, so you don't have to. But if you want to know where I looked them up, oh, I should probably put that there. Okay, so again, for the loading stuff, your cantilever beam is somewhere in here. Here it is. Oh, nope, that's not it. Yeah, it's over here somewhere. Simple beam, simple beam. Fix at one end, support at another. It's around here somewhere. Oh, here we are, cantilever beams. Okay, so you'll figure it out with one of these ones that says cantilever beam. Okay, so there's that. So you should be able to find the formulas for that. And steel shapes. Okay, so here's my W yada by yadas. Okay, so all the stuff is up at the top here. And if you want to use SI units, because the SI units are better, here they are. And you can just fill it in from some of these big crazy numbers. Okay, hey, if you want to use the S shapes, which are not wide plan shapes, they're not W shapes, you can use them instead. All right, so you just take it from here, put it in here, and use your own. Good. Okay, now I'm going to take all of these things from this thing, and I'm going to put them in one big dumb cross-sectional area vector. So I'm going to call it area params, and equals, open this up here, And I'm going to, there's a thing I can't remember how to do, but so I'm going to type in that. There we go. So it recognizes that. And there is, now there's a way, and I'm trying to remember, but we'll see how it goes. Anyway, it's pretty easy to do this. Oh, yeah, I already set this up. Copy. Copy, paste. Yeah, this part you might want to speed up a little bit. Okay, so finally, I'm gonna go all the way to our X and cap that off there. So that's our biggest vector that we're making out of that. Okay, so next, material properties. So we're going to go with the elastic modulus. So E, and so what I'm going to choose first is I'm going to make sure that I've got, I'm going to be using TI6AL for V. So E of that is going to be, let's see if I can find that over here, elastic modulus. Okay, titanium alloys. Well, it's anywhere from here to here. So I'm going to specifically look for elastic modulus TI6AL 4V. And this is from Parts Badger. Azom is a pretty good place to get things. So here it is. Where'd it go? Young's modulus, okay? Like I said, sometimes they call it that, sometimes they call it something else. Okay, and these are all in minimum maximum value in imperial, or I call it US units. So it's anywhere from 15 to 17. Let's just call it 16. And doesn't even give you the, okay, the units are 16 times 10 to the 6 psi. So that's 16 million psi. What did they have? Okay, 16,500. Okay, we'll go with whatever that is. Okay, 16,500. So E of TI6AL for V, oops, for V in PSI equals 16,500. Okay, so that's 16,500,000 psi. Okay, great. Next, yield strength. So I'm going to call it SY of and that's also going to be in PSI. And we're going to go over here and let's just assume that this is right. So our yield strength is 170,000 psi. Oh, that's the ultimate. I want the yield, so it's 160,000. Let's see what ASOM has to say. Elastic limit. That's pretty much it, the elastic limit. Okay, and it's got it at, oh, that's definitely less than that in KSI. So so the maximum tensile strength is way up high like this. So that's too far. Definitely don't want that. So we're going to go with the elastic limit here, the 114. So 104, and that's KSI, which is kips, as I was saying before, per square inch. So that's 1,000 pounds per square inch. So you got to tack on 3 zeros there. All right. And just our materials property vector. And again, I am missing all sorts of comments for every single step of the way. You should label everything really well. So mat prop that equals, so here's my vector. And I'm just going to copy this. And copy this. Nothing like watching somebody else program, is it? Yeah, like total nap time. Okay, so now that is the second major part of the whole thing, setting up the variables. So we did force, the length. We found the other parts too. So I should probably put this in here. V shear force, M bending moment. Unless that, did I already include those down there? Oh yeah. Okay, but I'm going to make sure that you calculate those too. Okay, so that's why I put those in there. Okay, so we started the script, created all of our data vectors, and now we want to all the input data vectors. Now we want to create data vectors for output. So next step is Okay, so now we're creating data vectors for output. And I don't know why that line showed up there, but okay. So a whole new section here, and we are going to find the flexural stress. So that is the sigma thing up here. No, wrong sigma thing. Here it is, the bending stress. Should probably make that flexural. Okay, flexural stress, shear stress, deflection, and output variables. So let's do that. So I'm going to call it flex stress beam in PSI, and it's going to be just our formula. For me, it's different because I'm doing the simply supported. You are doing the you're doing the cantilever. So my flexural stress is going to be, where to go? This one? No, this one. Okay. So mine's simply supported right here, concentrated load at center. So my Oh, it doesn't have the stress there. So, but mine is M times, oh, mine might, it shouldn't be any different. It should be M times M over S. So I'm going to be doing M in kip feet. But wait, that's in feet. Everything else is in, I want to make it in inches. So I've got to multiply by 12. And then on top of that, I've got, I did the 1 in kips, whereas I want in PSIs here. So I've got to multiply by 1,000 pounds per kip. All right, so watch out for that. And then I'm going to divide it by the S, which is this one right here. Good. Okay, so there's that one. And then there's shear stress on beam. And that's also in PSI. And that is to be 3V over 2A. So I can just use 1.5 times, so that the 1.5 from 3 halves, so 3 over 2 is the V. So I want to multiply it times this, V kips, okay. All right, times, oh, wait a minute, that's the wrong formula. That's for a rectangular cross section. I'm not using a rectangular cross section. I'm using something like this. Okay, so I need to use the other formula, which is V over dt. It's approximate. So that's why I'm not using that. So V divided by D, which is our web depth, there you go. D times T, which is our web thickness. There you go, copy. Okay, so I've got the right number of those. Oh, I should probably put that there and that there. Okay. So that's my shear stress for the beam. Good. Next. Deflection. Oh, wait a minute. Did I make sure I've got the right units? Oh, this is kips, and I want it in pounds. So times 1,000. Okay, anything else? That's inches, and that's inches. Okay, so we're good there. All right, so that's the shear stress. Let's deflection. Deflection beam PSI equals, all right, so our deflection over here is going to be like this, concentrated loaded center, and delta max is right here, PL cubed over 48 EI. So equals P, which is way up here, times L, which is also way up here. But uh-oh, that's in feet. That's why I put units there, to remind you. Feet times 12 inches per foot, but that has to be raised to the third power. So I want it like this. All right, so now I've got that PL cubed divided by 48 times E, which is this bad boy here, times I. Where'd I go? I have a thing up here. Aha. All right, so 48 EI. See if I got that right. PL cubed over 48 EI. Okay, that looks good. All right, so next is, okay, so now I want to calculate, let's see what's next on that list there. Okay, variable, okay, create a vector for the output variables. Now I also created a fraction of the yield stress. So I'm going to create a variable that gives the fraction of the yield stress created. Okay, you'll see what I'm saying. So we've got a yield stress that we don't want to go over. We definitely don't want to come close to it. So what fraction of it did we get to? So let's go look at that. So yield fraction beam, and there's not going to be any units because I'm going to divide one by the other, equals this one, this new one here that I've got. Oh, not shear stress. I want flexural stress. Copy. Paste. So it's going to be this flexural stress divided by the yield strength right here. And now that they're both in PSI, we can at least know that we have it properly taken care of. Okay. Last but not least for this one, we're going to create a vector for the output variables. All right. And oops, that should be yield, not yields. Okay. So stress vector, stress and deflection. We'll just call it that. Equals, open up a bracket, and we're going to put these find variables in there. Okay, again, this is the part where you might want to speed up, unless of course you make a mistake or a change, then you're screwed because then you missed that, but that's okay. All right. Okay. Now, going to start a whole new section here. So we're almost done. Display the results using Fprintf. All right. So I want to make it look good. That's why I'm using Fprintf. There's a lot more things that you can do with that. So again, comment every step of the way. Oops, must not have put the semicolon in there. Okay. So Fprintf, and going to say the following vector shows the beam loading parameters. Okay. And where are we at? Of force, length, shear force, and bending moment. And since I have it all the way over here, now I'm just do in units of kips, feet, kips, and kip feet. Then I put a /n here that helps it skip a line. Otherwise, it just jams things one on top of another. So I'm going to do that twice. /n brings it down to the next line, /n brings it down to the next line. So I kind of have a gap in the lines there. So that's always a good thing to make it look good. All right. And let's see if I've got that. It's got somehow it's got an issue with that. Let's see what the and then I display. Oh, I've got to have another I think that's what I missed. There it is. Okay. Yep. Watch out for that single quote. Don't put the double quote in there because Lord knows we can't have that. All right. And then we're just going to display the, what's that load vector called? There it is. All right. Then I'm going to do something similar. And instead of showing that, following vector shows the beam cross-sectional parameters. Of designation, linear weight, area, depth, web thickness. So it's all description. AMOI, section modulus, and radius of gyration around the horizontal neutral axis. Oof, lots more to go. In units of PSI or inches of appropriate exponent. Okay, good. There we go. And then then we display that area parameters. Oh, I guess I didn't put that on there. Copy and put that there. There we go. Now we're going to display the output. So again, another comment. I'm leaving out all the comments, and you should have pretty much a comment for every line that you go through. Okay. Okay, I can't spell. So introducing what's coming next. And Okay. Maximum flexural stress is, okay, so this is where you got to slow down. Okay, take it off the 2.0 or whatever it is that you're speeding through here. This is where we want to make sure that we're doing the right thing here. So we're going to put in a percent 5.0 F. Okay, this is floating point designation PSI. Okay, what this tells MATLAB is that there's a variable coming and I want you to put it in a certain format. So that's what we're doing right here, is that the percent 5.0, we can get into what that is later, is the format that we want to put it in. So the variable that's coming is this one. It's the flexural stress. Copy there. Boom, there. And oh, I forgot to put, oh, very important thing here. Of anyway, PSI, and that's got to have should have a period after it because it's the end of the sentence. But then we put in that, that next line kind of thing. But then I had forgotten to, as always, put in that single quote. Now it's going to use flex stress beam PSI and put that in for that variable that was in that thing. But which one is it? Okay. Okay, so that's, oh, I'm sorry, I should not be doing that flex stress beam PSI. I want you to use that vector. So we're gonna use stress deflection. So make sure you use this. Okay, stress deflection, but which one? We're gonna use the first one. 1, 1. All right. And all right, so again, this whole Fprintf thing, blah, 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 is is an important thing, but we can throw a variable in here. So that can get really handy at times. And but this is how you throw that variable in. I'm going to copy this whole thing because it's going to be a whole lot easier to do if I did it right the first time, then hopefully I did it right each of the rest of the times. So the maximum flexural stuff, what we want to do is change this to shear stress and instead make this 1, 2. And then do the same thing. And instead of shear stress, deflection. And now we want to make sure that that's not in PSI. That deflection should be in inches. All right. And hi, I'm recording, babe. And then we've got maximum flexural stress. Okay, the ratio. That's what the last thing is, the ratio of maximum flexural stress to yield strength is, and we don't have any, oh, look, yeah, so we don't have any ratio, or sorry, we don't have any units on that, so we don't want PSI here. And is that, and let's get that, give it a little space there, and we're gonna want stress deflection 1, 4. So that's our yield fraction on the beam. There it is. Okay, so that should pretty much cover it. All right, I see that I've got some issues here with some, oh, it might be missing a closing. Let's run it and see what happens. All right, so I should have run this a long time ago, but let's see what happens. Okay, so next thing you do, I should have saved it a long time ago, but yep. So let's see what we can do with this. And we have a problem. Line 46, column 7. Hey, I got all the way to line 46. Not too bad. Column 7. What is this? AL. Oh, I think I can't use dashes. Okay, well, there you go. And let's try that. And still wants semicolons. Okay, put semicolon there too. Let's see how that works. Oh, there's a dash there. Should have changed all of them, but I guess it didn't. Aha. Yeah, that's why it had some problems with that. All right. Yeah, I forgot about that. Living the, oh, I got some more here. Okay, anything else? Doesn't look like it. Looking for those red things there. Okay. Yeah, you can also look for errors over here. They'll show up. So it might be missing a closing. So I'm going to go to line 58. And is it missing a closing? I think it is. Yep, there it goes. And notice how that line went away. So I'm going to go up here. Okay, so don't worry about that one. That's way at the top there about the whole clear all. I think it's important. Okay, let's try to run it again. Line 66. I must have just had a weird thing. It got all the way to line 66. And oh, that's because I didn't put the slash ends inside. All right, so let's see how that goes. Hey, didn't have any errors. That's good to know. All right, so if you'll notice, my stresses are actually very, very low. And that's why I have a very small deflection and very small yield strength. So let's go to, yep, so I can go back up here, change my kips instead of 25 to 250, save it, run. Okay, so then my stress goes up a lot higher, but I have very, very minimal deflection, at least not on I think I just have it to set to a certain number of, I think that 0 is, oh, that's what that 5.0 is, as I wanted to, I was going to tell you guys about later, but 5.0, that's how many decimal places, you show on to the left and then to the right, or sorry, figures you show to the left and to the right. So that makes sense when you're talking about like thousands of stresses, but my deflection is going to be very, very small. So I'm going to put this at 3, and then my ratio is going to be hopefully significant there. So I'm going to change that to 2, hit save, hit play, and aha, my deflection is still really, really tiny, and my yield strength is 0.1. So sorry, so I haven't really come very close to the maximum yield strength on this, which is fine in terms of a design. But I'm wondering if the deflection, there's something wrong with the deflection. Oh, I did not multiply it times 1,000. That explains it. So let's hit save, and then let's hit run again. Aha, so now I have a small deflection of about 1/20 of an inch, and my flexural stress is about 10% of the yield strength. So still, even 250,000 pounds on a beam, this is really a gigantic beam. It's like almost 30 inches deep. Okay, so it's 2.5 inches. It's 2.5 feet tall. So it's a very large beam made of extremely strong titanium. So of course you'd never actually get that because it's ridiculously expensive. But so hopefully I was able to show you a couple things about debugging, how MATLAB works, and how to set up some vectors that are meaningful, and how to show these calculations to make that happen too. So you see that in your workspace, these things show up. You can see the values. And also, I think I hope I showed you good techniques in how to program and setting up your variables so that they're meaningful and you can see what they are. Now, it's up to you to do all the commenting of your very own, and I look forward to seeing your work. Have a good day.